Hi there, guys. We're gonna go ahead and have Rick get started here. He's gonna.
Oops, sorry. I, I meant to unmute. Let me introduce myself and the program tonight. Welcome to the Virtual Night Sky. Uh, this program is presented by the School of Earth and Space Exploration. We are part of Arizona State University. And my name is Rick Alling, and I am a manager of public outreach programs. In the background behind me, you see in my virtual background, that's a place we call the Marston Exploration Theater. It's usually a very public place. It's very active. We have lots of crowds come in and see programming in this particular building. And of course, during COVID, we're not doing that right now. So we're open for classes and students are attending ASU, but we're not doing public programs yet. Soon to come, and we'll make sure everybody knows when that's going to happen. But until then, we're meeting every other Wednesday night in a virtual program where we can kind of just explore the night sky together. We can explore earth processes together. We can do all kinds of different things. We try to give everybody something to look for, something to do, and then come back and visit us 2 weeks later. And so tonight is one of those nights. Here's how this is going to work. We are going to just kind of visit a part of the sky that we've been noticing for the last couple of months. Many bright stars. I'm going to reacquaint you with some constellations and some stars that we're going to be talking a little bit deeper about tonight. And then we have a very special guest. Dr. Patrick Young is in our program faculty at the School of Earth and Space Exploration, and he's going to talk to us a little bit about color of stars, what that means about the surface temperature of a star, and what that means about the evolution of stars. And so we're going to compare what we can actually observe from the ground, like from your driveway, from your backyard, and what we can understand about the stars as they exist in space. And then we'll do some question and answer and some polling. And then at the end of the program, we'll kind of give you a view of what we're going to be talking about in the next couple of months. And that's how we're going to do this tonight. So let me introduce some of the people that are along with me. My colleague is Meg Hufford. She always joins the programs. And she and I are the people that would be meeting the public if they're coming to campus and coming to visit our building. So now we are scheming to do virtual programs, not only these Wednesday night programs for you, but we also put together programs to go into classrooms, K-12 classrooms and other places. And so we're trying to keep our outreach going. We're trying to stay in front of people, and we're doing it in meaningful ways, but virtually at the moment. Kim Baptista is your webmaster. She is also part of the community outreach group, and she's the one that has organized the program, the technical part of the program, the communication, and working the lists and making sure that everybody's aware of what's going on. And so she's on the line tonight. And then 3 students tonight. So Alex Blanche and Alicia Hyatt. You'll see them a little bit later. They will be kind of working through some audience questions and some polling as we go through the program. And also Spurti Cassere is also with us tonight. She's going to be working the background, fielding questions. We don't open chat for this particular Zoom call, but we do invite you to do questions. So there is a Q&A button on your screen. And if you go in there and just sort of like just write out whatever you'd like to hear about, we'll try to field those either in the background or bring them right in front of the audience at question and answer time during the program. If you happen to be a student, I always love to hear that you are, I am so-and-so, don't give me first, last name, but you can say who you are and what grade you're in, and use that to preface your question. We really do like to hear from school age kids as they do this. Speaking of which, if there are teachers in the audience and you would like to have visits to the classroom, then make sure you use the links available to you and get back in touch with us, not only by virtue of how you got into the program tonight, but we'll also send a survey out at the end. And if you have something you'd like us to do, if you'd like to have us talk to you about some of the different programs we do, what we can bring to you. Let's do that afterwards. And so welcome everybody. I know we always have a bunch of new people, and so welcome. I know we have some followers that have been with us every other Wednesday for some time. We're almost going on a full year. And that's kind of exciting because the way the sky works is that we cycle around in annual cycles. And so we're almost within several weeks of getting back to the place where we started last May and June when we started this program in the first place. And that's kind of exciting, an exciting milestone, because in some ways we can start over, in some ways we can just add new things as we go along. So this program is going to go on. If you set your schedule and want to do this with us every other Wednesday, I think that would be very cool. All right. I'm going to, here's what I'm going to do is I'm going to take just a real quick moment and share a screen with you. This is on an iPad, and I use a program that you can get at home. It's just a little planetarium program. I'm going to use it tonight to essentially give us a little sort of view of of the sky, and show you some of the stars we're going to be looking at, and I'll kind of just walk you through. This is something of a reminder. If you've been with us before in the last month or so, you know we're looking at a particular part of the sky that has really very bright stars, an easy part of the sky to get to know. And I just checked just before the program. I thought clouds were going to come in, but they've stopped. They're not coming in, at least from my house. I'm starting to see this part of the sky right now. So you can see from my the way I sort of do this, and there's a you can see everything that is green is below the horizon. Everything that's within that circle is above your head right now. That's in the night sky, or I should say at 8 o'clock when we're done with the presentation tonight. This is what the sky is going to look at. So I'm going to direct your attention towards the south. Let me just sort of get the horizon lined up like you're used to it. And you can see two really bright stars there. Canopus is actually just right above the horizon. So unless you have a really clear view of the southern horizon, like you're on South Mountain looking south, you're probably not going to see that star. But it does just rise just above the horizon, crosses that south meridian line, and then goes back down. And it does that this time of year. It's a very, very bright star. We don't usually use it or include it in some of star walks and star talks because it is so close to the southern horizon. We just don't see it very well from where we are. Just above that, though, you can see there's a cluster of very bright stars. What I'm going to do is take a quick little screenshot here so that I can sketch and draw. And I'm just going to walk us through what we're talking about. We are looking at a part of the sky that is, should I be red? No, I think I'm going to try to be white. And so if I kind of draw a big, huge circle here, what you see is contained within that circle is a huge cluster of some of the brightest stars in the sky. And I'm just going to walk you through some of them and circle some of them because they're going to be part of the discussion tonight. And then I also want you to notice that as you look at this particular depiction here, the stars have all different colors. Now, these are exaggerated in this little planetarium program, but stars do really have different colors. And let me just show you a little place where you can look to see that very importantly. I think most people know the constellation of Orion. Orion is the great hunter. It's marked by these belt stars, the three stars that make up Orion's belt. But the important ones we're going to be looking at tonight, or included in the important ones we're going to be looking at, there's one of the upper shoulder. It's called Betelgeuse. And you can notice it's actually an orangish reddish kind of star. And so after the program tonight, that's going to be part of your assignment, is to go out and find Betelgeuse and then find the opposite on the other end of the belt, or other side of the belt, just the opposite. That star is called Rigel, and it's going to show very blue or whitish blue, probably have a nice blue tint to it. And if you look at the two stars together, I mean, this is visually, you in your backyard, you in your driveway, finding these two stars and look at them, you can definitely see the color difference, or I think you can. Most people can do that. And so that's going to be kind of part of what we're talking about and part of what we're going to do tonight. Orion is a big player in our sky. Way up over here is a constellation called Orija. It is a charioteer, and it also has a bright star called Capella. Over here is the constellation Taurus. Here's the head of the bull, and his horns come up this way, and this basically is Taurus, the bowl over here, and Aldebaran is a bright star in Taurus, and that will be part of our talk tonight. In this particular part of the sky, we're going to talk about this now, and I'm going to talk about it again at the end of the show, but there's a triangle here. We call it the winter triangle. These are bright stars in 3 different constellations. It anchors on Betelgeuse, that shoulder star at one end, but Sirius is the brightest star in the sky, brightest star anybody can see in the sky, and it's up right now, and that's right here. And then over here is a star called Procyon. Procyon is part of a little constellation called Canis Minor. That's the little dog. Sirius is probably part of another constellation called Canis Major. That's the big dog. And then in between all of these, the part of the sky we have left out so far is Castor and Pollux. They are the twins. Gemini, part of the zodiac. It's the zodiac sign that comes after Taurus, the bull, and Gemini, the twins, are right there. So here's, just before I introduce Patrick and talk about this, we classify stars by their color. So the surface temperature of the star provides its color, and that's the system we use for classification. And we use a letter classification to do that. So I'm going to actually just show you the ones we're going to talk about here, and then I'll get rid of my screen, turn this over to Patrick. But right here, the belt star that is at the very, on the very right is a star called Mentaka, and you'll find out that there is a O star component in there. And then Sirius is a B star. And I'm sorry, Rigel at the bottom knee of Orion is a B star. And A star is Sirius. F over here is the letter classification for Procyon. G is the classification for Capella up in the top part of your screen. K is the one that is associated with Aldebaran, and M is the classification that's associated with Betelgeuse. So I don't want this to be confusing, but that is all of the classification types are represented in the sky tonight. We use those letter designations, and to learn more about that and hear more about the surface temperature of stars and what all this means, I am going to stop share, and I'm going to introduce you Dr. Patrick Young. He is an associate professor at the School of Earth and Space Exploration. I've known him for a long time. He's a good friend. He's a good colleague, and he happens to be the boss. He is the faculty leader of the community outreach group, and that's where myself and my colleague Meg and my colleague Kim Baptista actually operate. So let me stop the share here, and if you can come online, and I'm going to turn the microphone over to Patrick Young. Thank you, Dr. Young.
Thank you, Rick, and thank you everyone for being here tonight. I'm excited to do this. The part of the sky that you've been touring with Rick is one of my favorites because you can actually see an example of almost every kind of star and almost every stage of stellar evolution. And I'm excited to be talking about color because not only is it a fundamental property of stars that tells us an enormous amount about them, but I've also done a little bit of research on perception and linguistics of color in stars. But to start out, of course, we have to ask ourselves, what determines a star's color? We have Betelgeuse up here in Orion, and Rigel down here in the bottom. Very different color. Of course, this is a photograph with a long exposure. It's enhancing everything. But if you go out at night, you can see the orange tinge in Betelgeuse. And it turns out that what determines a star's color is temperature. So I want to show you a little simulation here that gives you an idea of how a star of a given temperature emits colors. And what you'll see is properties of the star over here, how the star would look to your eye approximately over here, and in the center, the intensity of the light that's being emitted at different colors. So from here to here are the colors that we can see with our eye. Further out is infrared light. Further in this direction is ultraviolet light. And the star we're looking at here is approximately the temperature of the sun. And so the sun actually emits the most amount of light here at green wavelengths. But that's not what we see. The sun basically looks white, maybe a tiny bit yellow to us. And the reason for that is you're seeing all of these colors of light added together at once. And evolution has trained our brains to perceive normal sunlight as a white color. So let's try looking at a star that's a bit hotter. So this would be something like Rigel. And it actually puts out most of its light in the ultraviolet. And we're just getting this little tail down here in colors that we can see with our eye. And that amount of light is growing and growing as you get to these bluer and bluer colors into the ultraviolet. So what we see with our eye is a blue colored star. Going in the opposite direction, we'll look at something that is more like the temperature of Betelgeuse. And that's this curve down here. So the color at which such a star is producing the most light is right at the edge of the red we can see. And a lot of its light is coming out in the infrared. So when we look at that in the sky, we see it as a distinct orange or even red color. So knowing that temperature determines a star's color, now we have to ask ourselves what determines a star's temperature. And to do that, we need to step back and ask ourselves, why do stars shine at all? Now, stars are tens of thousands to tens of millions of times the mass of the Earth, which means that gravity is really not a friendly thing for them. It wants to compress them down into a little tiny ball. But when you compress a gas or a plasma, that heats it up. And if you have a hot gas, it has pressure that makes it want to expand. So those two forces counter each other, and the balance between them is called hydrostatic equilibrium. Now, another property of a hot gas, or actually anything with a temperature, is that it glows. And stars are looking out on the cold blackness of space, so they are emitting light out into the universe all the time. And the reason that stars do pretty much everything they do is because they have to produce energy to replace the energy that they're shining out into space so they can balance themselves against gravity. And because they have more gravity to fight against, more massive stars are brighter. The brightest ones are millions of times brighter than the sun. And to be bright, a star either has to be hot, because hotter objects are brighter, or it must be large in radius, so that it has more area from which to emit light. And a side note that we'll see later is, since massive stars have to produce so much more energy, they use their fuel faster, and they live lives as short as a few million years, whereas something like the sun lives more like 10 billion, and the smallest stars can live trillions of years. But for the moment, let's get back to our size and color in general. So this is a nifty graphic that starts out with Jupiter here as a basis of comparison, and goes to one of the smallest stars, which it turns out is actually not that much larger in radius than Jupiter. Then we go to our sun, and we go to Sirius and Canis Major, and then we go to Pollux and Gemini, with Sirius now shrunk down so we can see the right relative scale, to Arcturus, to Aldebaran in Taurus, shrink that down, and then we go to Rigel, Antares in Scorpius, and Betelgeuse. Now, if you drop Betelgeuse in the solar system in place of the sun, it would swallow everything out to about Jupiter. But it is not at all the largest star that we know of. Probably the biggest one in terms of radius that we're aware of is VY Canis Majoris, and that would happily swallow up Saturn and actually go a bit out beyond that. But in terms of what we can see with our eyes and be really noticeable, Betelgeuse is about the biggest thing that we can see. So stars get this energy that they need to survive from nuclear fusion. And the structure of the stars changes as they use different fuels. 90% of their lives, stars are turning hydrogen into helium. We call this the main sequence. And the pattern that we see is pretty simple. The more massive your star, the hotter and the brighter it is. But once stars run out of hydrogen and start doing things like turning helium into carbon, and they evolve to the later stages of their lives, they usually become significantly cooler than they were on the main sequence, and usually brighter as well. And I'll talk just a second about what's going on in the interior of stars, because this is one of my favorite areas of research, and that's the synthesis of the chemical elements on the periodic table. And the first stage is we take hydrogen, the lightest, simplest element, and turn it into helium. That's what our own sun is doing right now, has been doing for 4.5 billion years, and is going to do for another 5 billion or so. When it runs out of hydrogen, it's going to start turning helium into carbon and oxygen. And that's what Aldebaran is doing. It is a red giant. However, stars like the sun and Aldebaran never get past the point of making carbon and oxygen. In order to turn carbon into heavier things, you need to have a star about 8 times the mass of the sun or more. And Betelgeuse and Rigel are excellent examples of this kind of star. And this is actually an image of Betelgeuse. It's so big and relatively nearby that you can take a resolved picture and see the disk of the star. So this is what one of those massive stars looks like in the later stages of its evolution. It's probably doing that helium burning stage. And there are steps past that. You turn oxygen into things like silicon and elements near it on the periodic table, and take silicon and turn it into heavier things up to iron. And these take shorter and shorter times. So the lifetime of Betelgeuse on the main sequence is about 8-10 million years. The time scale for burning oxygen is about 6 months. And you turn something like twice the mass of the sun from silicon into iron in the space of a day and a half. So we actually can't observe these last stages and know for sure they're going on, so we have to do computer simulations of them. And then when you get to iron, you have a problem. Iron does not produce energy at all. So that is effectively the end of a star's life. And it would be great if I had time to talk about supernovae. Those are one of my other favorite areas of research, but I'm afraid we're going to have to skip over that. So we know a little bit about why stars have different temperatures and different brightnesses. How do we use that to classify them? Well, the person who came up with the classification according to temperature, which is the spectral types that Rick mentioned and which we'll talk about, was Annie Jump Canyon. She started at Harvard as a computer, which is the word they used for women who did all the research and got none of the credit. But they eventually recognized that she really deserved to be a PhD astronomer and a member of the faculty. So she did eventually get recognition. And what she's recognized for is cataloging 350,000 stellar spectra by eye, looking at photographic plates. And with all that effort, she developed a classification called spectral type that we still use today, which classifies stars according to temperature. And when we add luminosity as a dimension to our classification, we can put stars on something called the Hertzsprung-Russell diagram. So the vertical axis here is luminosity, and the x-axis is temperature. Now, one thing to keep in mind is that in this figure, high temperature is on the left, low temperature is on the right. And that is for historical reasons, which is the standard excuse when something doesn't make sense in astronomy. But nonetheless, this is how we use things. So if we look at this diagonal stripe here, that is the main sequence. And as we go down the main sequence, we see these different spectral types. O is the hottest, and we go through B, A, F, G, K, and M. And each of these has a subclass. So the hottest B stars are zeros, the coolest are 9, and then you transition to A stars, for example. And there are also luminosity classes. The supergiants, the brightest stars, are class 1, and that goes through giants at about class 3. The main sequence are class 5, and then finally the little white dwarfs, which are stellar leftovers, are class 6. And as a star goes through its life, it can move through this diagram. Stellar evolution changes the temperature and it changes the luminosity. The sun here will get brighter as it goes, and when it exhausts its hydrogen, it will start to move to cooler temperatures and get brighter. Similarly, for something like Rigel, it will start over here, move all this way on the main sequence, and then when it runs out of hydrogen, it will go even further and become a red supergiant. So usually when we see stars over here that are bright and cool, those are evolved stars that are nearing the end of their lives. And now we're going to see examples of all these different spectral types in what I like to think of as the Virtual Night Sky Stellar Evolution Lab. Here you see all different stages of stellar evolution. If we go down to the sword in Orion, this brightest thing here is not a star, it's a nebula. And that is a cloud of gas and dust where hundreds of new stars are forming. So we go from protostars here to main sequence stars, which are most of the ones you can see. So something like Procyon is a star not too different from the sun. That is on its main sequence. Aldebaran is also sun-like, but it's a red giant moving towards the end of its life. Similarly, Rigel is a main sequence massive star. Betelgeuse is a red supergiant, a evolved massive star. And Procyon and Sirius both have white dwarf companions, which are the end states of low mass stars like the sun or Aldebaran when they run out of fuel. And right about here between the horns of Taurus, you can't see it with your naked eye, but with a moderately sized amateur telescope, you can see the Crab Nebula, which is the remnant of a massive star that exploded as a supernova about 1,000 years ago. And in fact, if you look at the image behind me, that is a record of the Crab supernova from Chaco Canyon in northern New Mexico by the ancestral Pueblo. My apologies, the ancestral Puebloans. So looking at individual examples of our spectral types, we'll start out with Mintaka in Orion's belt. This is an O9.5 star, and it actually has two large, somewhat cooler companions that we can't separate with our eye or a wide field image like this. It's about 25 times the mass of the sun, a couple 100,000 times as bright, and about 5 times as hot. So it sits here in this upper left corner of the HR diagram. And this is a star that's on the main sequence burning hydrogen, and it's a few million years old. When we move to Rigel, we are looking at a B star, and it is getting over here into this supergiant territory. And it also has two cooler companions. This is Rigel right here. It's a little bit less massive, 20 times the mass of the sun, a little bit less luminous, and only about twice the temperature of the sun. It has moved close to the end of its main sequence lifetime at an age of about 8 million years. Now things are going to look different when we get to Sirius here. Sirius is an A05 star, which is pretty much the standard against which you compare everything else. And it has a tiny white dwarf companion. You're noticing a pattern here. The vast majority of stars are in multiple systems. The sun is actually pretty weird not having a companion. Sirius is much smaller than the ones we've talked about before. It's only twice the mass of the sun, 25 times the luminosity, and it sits down here on the main sequence on the HR diagram. And here we get a really big reminder of how massive stars and low mass stars differ. Rigel was getting to the end of its main sequence lifetime at 8 million years old. Sirius is in the prime of its life at 242 million years old. Moving on to Procyon, we have the smaller dog, and we have a smaller star. This is an F5. It also has a white dwarf companion, and it's about half again more massive than the sun. Getting down to the point, it's not too much more luminous. It's a little bit hotter. Sits here on the HR diagram and is reaching the end of its main sequence lifetime, almost 2 billion years old. When we get to the G stars, we have to move away from the main sequence. They're getting dim enough that there are not a lot of them that are visible to the naked eye in the night sky. So we turn to giant stars to actually show off these later spectral types in the sky. And when we look at Capella, we're actually seeing two giant stars, a G3 and a cooler K0 star, with two tiny companions. They are both about 2.5 times the mass of the sun, 70 or 80 times the solar luminosity, and they differ in temperature by about 800 Kelvin. And these stars sit over here. They are red giant stars, a little bit before and a little bit after the primary red giant stage. And the reason that the slightly larger star is also cooler and brighter is because it is at a slightly later state in its evolution. They form together at the same time, but remember, a more massive star moves faster through its life. And while we're talking about G stars, there is one main sequence one that is really easy to see, but not in the night sky. Our sun is a G2 main sequence star. When we get down to even cooler stars, Aldebaran is a K star. And once again, we have to go to a star late in its evolution, because K main sequence stars are way down here at 1/10 or less the brightness of the sun. They're very common, but you just can't see them with the naked eye. So Aldebaran is just a little bit more massive than the sun, but much brighter and much cooler because it has long since depleted its hydrogen and is now turning helium into carbon and oxygen in the core. And it is about 7 billion years old. And then finally, to show off our coolest stars, we have to move up to a supergiant. The main sequence stars are way down here with 0.1% or 0.01% of the sun's brightness. But Betelgeuse, which is a 17 solar mass red supergiant, is of course plenty bright to see. It's 125,000 times the luminosity of the sun, but highly variable. These are two images taken in 2019, and you can see how much the star has changed over the course of a year. And it's very cool. It's 3,600 Kelvin. Compare that to 5,800 for the sun. And there is one other kind of cool thing about it. Think back to Rigel at the opposite corner of Orion. That was a little bit more massive, about 20 times the mass of the sun. Very similar in luminosity, but it was about 15,000 Kelvin, so 4 or so times as hot. It was also a similar age, which tells you just how fast late stages progress in these massive stars. So we are actually seeing two very similar stars, but getting to compare them at different stages in their lives. Rigel is on the main sequence. Betelgeuse is almost ready to die as a supernova. In fact, it's the nearby star that we can easily see that is closest to becoming a supernova. Now, saying it's going to go soon means anywhere between tomorrow and a few 100,000 years from now, but that's still pretty close in astronomical terms. And that's why after Rick finishes up here and you go out to see these things in your own sky, I want to invite you to join me in chanting, "Go, go, go," so I can actually see one of these things go off nearby during the course of my career. So now I will let Rick take over, and you can get on to helping a guy with his career. Thank you very much.
Patrick, we're going to do it. We're going to help you. I know we are. So, hey, I just had an observation and a question, because we kind of was Betelgeuse was acting strange last year, and I think you pointed out the dimming or the sort of our observation of Betelgeuse. But every time it shows something unusual, don't scientists go, "Oh my gosh, it's about to go. It's like this is the one. This is it, right?" And then they find out it really isn't going to go yet, right? So.
Well, the scientists who actually study stellar evolution do not think that that's going to happen every time the star changes, because the last stages of the star's life happen so quickly that the information about what's going on can't get to the surface. It takes a long time for changes down in the core, which is the size of the Earth, to get out to the radius of Jupiter. So when it goes off, good chance it's going to be a surprise. What happened to it in 2019 probably has a lot more to do with how energy is transported in the outer part of the star. That goes into a lot of details, but basically energy gets from down near the core to the surface the same way that hot water in a pot on the stove convects and the hot stuff moves up to the surface and the cool stuff sinks. And if one of those streams of flowing plasma collapses, you suddenly get a much cooler and darker part of the star, and the luminosity can drop before things sort of get back to their equilibrium state.
Yeah. Then the other observation I have is Betelgeuse is not really the only bright red star we get to see in the sky. So Aldebaran is kind of oranger and kind of close, but Antares is also a reddish kind of star. And so I think what I'm hearing from your description is all of the red stars that we actually can see, the ones that are visual, have to be kind of like these supergiants, because the red stars that aren't are very small, very dim, and they're just not visible to us at all. Is that right?
Yeah, they're all either giants or supergiants. The closest star to us, Proxima Centauri, is one of those little red dwarfs. And even though it's the closest star, you cannot see it with your naked eye.
Because it's just too small. Yeah, so that separation, I guess I've looked at that chart for years, but I never really sort of like figured, okay, that means that all red stars that we can see are probably towards the end of their lives and probably sort of have already left the main sequence, and that's all going on. That's really actually fascinating. And I will tell the audience that in the Marston Theater behind me, this is just sort of a little plug for Patrick and his work. We have had some students take some of Patrick's models of supernova. Remember, he mentioned earlier in his program that is also one of his passions, is how stars find their demise and how you model the final explosion and the final death of a star. We've taken some of those models and actually put them into a system where we can see them in 3D in the room behind me. So that's something to look forward to, because when we get back to school, when we actually have audiences coming back to visit us, I'm going to invite you to sort of like look up the Marston Theater, make sure you get to it, wait until we start doing programming again and get in there, because some of the things that we can see, research going on in stellar evolution and then in a 3D environment where we can actually sort of model it for people, it's really pretty spectacular. I think you'd agree, right, Patrick?
Definitely. It's so nice to see it in that format instead of on my little tiny computer screen.
Yes, I get it. Okay. I think the next thing I want to do is to basically kind of open this up for audience questions. So I don't know, I'm going to kind of have the team join in. Alicia and Alex, who have been monitoring questions. They're also going to kind of control some poll questions so the audience can participate. And we'll go to that phase of the program now. And then I'll kind of go back to another little night sky view in a moment here. So go ahead, Alex and Alicia, how you doing?
Hi there. So I'm going to go ahead and launch our first poll. There we go. And it says, have you noticed different colors of stars in the night sky? So go ahead and cast your votes down below. And while we're waiting on that, I'll maybe turn it to Alex for our first question.
Right. So we have a question from Nicole, and they ask, how do you know how old a star is? It's a very good question. Like many things in this wonderful field of space exploration, a lot of things are estimates, but they're educated. For stars, that's usually from other observations and our understandings of how stars evolved. We observed a lot of stars. We saw that HR diagram before, we kind of know the path that they take in their life, where they start and where they end. And so by observing a star, we can kind of match it to other stars we observed and our understanding of the entire history that they usually go through, and then estimate it from there. That includes, observing, their light emissions. That includes measuring their metallicity from that light emissions and then kind of going from there. But it's basically from all the other observations we've done in the past and our understanding of those.
Thank you so much, Alex. Alrighty, so I'm going to go ahead and end that poll for us. My question again was, have you noticed different colors of stars in the night sky? And a majority of us, 88% of us, have noticed a change, or I'm sorry, have noticed different colors of stars in the night sky. So that is absolutely awesome. Keep looking up. Rick, would you like me to keep going with the
Yep,
poll?
go ahead, please. Yep, go ahead. I think we have two more. We'll try to.
Perfect. So I'm going to launch this next one. The question is, what is the order of the letter classifications, hottest to coolest, of stars? So go ahead and cast your votes there. And while we're waiting for that, I'll have Alex answer another audience question.
So people were really interested in the idea of companion stars. And so Natalie asked, could Jupiter be the sun's companion in our solar system? No, Jupiter's a very, very large planet. It's the largest planet in our solar system. So it's the closest thing we have to another star in our solar system, but there's one missing difference, and that's nuclear fusion. So people ask, what's the limit between a really large gas planet, which is basically kind of made up of the same stuff as our sun, and our sun itself? And that's because Jupiter doesn't have enough mass. It's not dense enough at its core to begin the process of nuclear fusion. And that's what makes stars burn. That makes them give off heat and energy and radiation. And so Jupiter isn't large enough yet. I can't remember how much larger it has to be, but it's a good many times more before it can even begin to reach that process of nuclear fusion. So no, but it's very similar in makeup, but it's just the size that makes a difference.
Thank you.
It looks like everybody got this right. Look at this. The same 88%. Isn't that interesting?
That interesting. All right. Looking back at this question, it looks like everybody, or not everybody, but 88% of us were right in the order of the letter classifications, hottest to coolest of stars.
Okay, before you go on, right, we haven't used any of the mnemonics for this yet. So I'm going to tell you mine, and then Alex had one too. So my old school mnemonic to remember this is, oh, be a fine girl, kiss me. And you can substitute guy for girl if you wanted. So you can say, oh, be a fine guy, kiss me. That's how I remember the order. That's how I remember it. But Alex, we were talking the other day. What was that? What was the one you used?
So the one that I came up with was, only bad astronomers forget generally known mnemonics. Mnemonics being spelled with an M, so it fits barely. But that's my preferred one. That's how I remember it.
Okay, do only bad astronomers forget generally known
Mnemonics. Yeah.
Okay, I like it. I'm going to start using that one instead. Thank you very much. Now everybody knows. So you got one of these. And do you have one, Alicia?
No, but I'm going to use Alex's, not necessarily for this, but just as a vocal warm-up every now and then.
I get it. Okay, we have time for the other poll. Go ahead.
Wonderful. Great job. So moving on to our last poll, I'll launch that. And that question states, when we describe color, red and orange are warm, blue and green are cool. For stars, colors, and then go ahead and cast your vote down below for the end of that statement. With that being said, Alex, if you by chance have a third question you can answer for us.
I mean, I almost think that this poll question actually answers Pam's question, who asks, how do you determine the temperature of the star? And that's basically determined by its color. The specific peak wavelength of light that a star emits is a really good indicator of its temperature, and that's what we use. So this poll question actually gives you the answer to how we generally do that.
Awesome.
I have a question related that I want to take back to Patrick, if you can, if Patrick can come back on. So the surface of the star, right? Actually, what we're seeing at the very, very surface is sort of creating, if you want, the color that we get to see, the color of the light that's transmitted. But what is the temperature inside a star? Like, what's the inside of the sun doing?
Yes, the inside of the sun is a little over 10 million Kelvin.
Okay.
The smallest stars, it's a few million, and it gets to tens of millions in massive stars on the main sequence. Stars right at the end of their lives, like Betelgeuse, if they're burning helium, it's probably a couple 100 million. And if they're right at that end where they're burning oxygen or silicon, 2 to 5 billion.
Oh my
Kelvin.
gosh. Okay, that gets so it's a very, very big difference. So the actual fusion process, the thing going on really, really deep down inside the star, is much, much hotter. And by the time that energy convects or however it moves up towards the surface, it's diminished really quite a little bit. So once the surface is heated, that's the part we actually can see. Is that right?
Yeah, because basically you're spreading all of that energy over a much huger area, so the temperature at any one spot is going to go down.
Okay, I get. Okay, sounds good. Thank you. And so, what's the result of this poll? This is interesting. So we kind of at least have a little competition here.
We're going to get the answer to Pam's question right now. No wait needed. So the question was, or the question we proposed was, when we describe color, red and orange are warm, blue and green are cool. For stars, colors, and 63% of us got it right. The relationship is reversed. So awesome job.
Blue is hot, 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 and red is cool, 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 right? And so the coolest star is still hot, 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 I guess. But red stars are cooler than our sun. Blue stars are hotter than our sun, and it is kind of backwards from the way you remember in grade school where you learned about your colors and mixing paint and all that stuff. So it's just backwards. That's a good way to think about it. So, all right. Any more questions, guys, that we can go to, or are we ready to move on?
I think we're ready to move on if you are.
Excellent. I am going to share screen again, and I'm going to show you some stuff here. Let me see if I can do this. This is kind of clumsy on my iPad. I'll figure out how to do this better some other time, but for right now, I wanted to show you some astrophotography. And so I actually had a chance to go, and I know our audience, every once in a while we get requests about astrophotos and things like that. And so I had a chance to go up north, northern Arizona. We went to Pine Top Lakeside, just my family and my wife's sister and my brother-in-law. And we took our dogs and we sort of like had a cabin. And I knew this particular program was coming up. And this was only about 3 weeks ago. And so I started taking pictures of the part of the sky we're going to talk about. Does anybody recognize what's going on here? So you can see the trees, right? There's this new field of astrophotography. I really love it. It's kind of like this landscape astrophotography where you can have things going on in the foreground and have all these stars in the background. The little flare at the top where it sort of like seems like there's a little light trying to get into the thing. That's actually the moon. I tried to keep it out of the frame of the camera, but it's sort of still, moon is bright and it's sort of like reflected a little bit off the lens of my camera here. But you can see in this, you can see that, here's Betelgeuse, right? Remember that one? So, and you can see a difference. Here's the sort of the orangish kind of Betelgeuse, and then here's Rigel. And we've talked quite a little bit about those stars and that relationship. And so these will be up. I mean, right as soon as we're done here, I'm going to kind of close out here in about 5 or 10 minutes. And then I really think it's a good idea tonight. It's a good night to go out, take a look, find Orion, find its belt. That's pretty easy to see. Patrick was talking about this little sword thing that hangs off the belt. That's pretty easy to see. And this is a star in the bottom. It's called Saph. It actually means point of the sword, if you want to kind of like put that way. This one up here is called Bellatrix. And between all of those, it really does look like a great hunter. If those of you that remember, we had a program in December, and Spoo and Spurti and Alicia actually did a big description about Orion, lots of the pieces of Orion. But that's really a cool place to be. And then I'm going to actually also ask you to do something else. And I was going to just joke with you a little bit and say, you get to earn your MFA tonight. Okay. And I'll show you how. And because I did it by taking this picture, and you can go out and sort of like explore this thing. I showed you this at the very, very early part of the program, but Betelgeuse up at the top over here. And Sirius, which is the brightest star in the sky, and Procyon, which we learned about tonight. If you just kind of connect them all together, you get this really beautiful, big, huge, giant triangle. And now that you saw the program, right, you actually sort of know that one of those stars is an M-type star, one of them is an F-type star, and one of them is A-type star. Now, you might not have been following close enough, but I'll just sort of remind you here. So the M star belongs to Betelgeuse. The F classification belongs to Procyon, and the A classification belongs to Sirius. So if you find that triangle, you find those those 3 stars, you remember the letters, then you too can earn your MFA in the night sky. Do you want to try that tonight? I think you should. And then I'm going to show you one more thing before we close tonight. This is same night. That's looking one direction. This is sort of looking in a different direction. You can see another tree in the sky. And I hope you're sort of savvy enough now after watching our program a little bit. Can you find, before I point it out, can you find the Pleiades, the little sort of 7 sisters? We talked about that a couple of weeks ago. And the Hyades, which is the head of the bowl. Let me sort of just organize to sort of like sketch them for you if you want. I'm going to use a different color this time. I'm going to use red. And so the Pleiades, the 7 sisters, are right here. This little V shape right here is the head of Taurus the bull. And this star right here, you learned a little bit about today. It is a K-type star. It was the one that Patrick used as that example, and it's called Aldebaran. Now, look down here. You see this little sort of object right here? How many of you know what that is without me sort of pointing it out to you? Anybody know? Okay, that is the planet Mars. So if you were watching a couple of weeks ago, we were talking a lot about the Perseverance rover and its landing on Mars and all of that excitement. And so here's Mars in the night sky. And this was taken a couple of weeks ago. I was kind of up in the woods, and this is sort of what we were looking at. Mars has now moved, and what we're going to do is we're actually going to follow it in this direction. A couple of nights ago, it went past the Pleiades. Tonight, you're going to find Mars is right here next to these 2 stars right there. And over the course of the next several days into the weeks, Mars is just going to kind of continue moving through the sky and up in this direction, splitting the bull's head and the Pleiades and moving up there. And the real important reason to watch Mars is because it's moving away from us, so it's getting dimmer. It will be very much the same color as Aldebaran. So watch for this tonight. I showed you how to find that big triangle. That's one thing. But find the Pleiades, find that V-shaped head of the bowl, and look for Mars right between them tonight. And then go out night after night after night. This is really a really cool thing to see, because you'll see the movement of Mars. You'll see it actually sort of like moving through the sky and moving along. And then while you look at the surface of Mars, remember, we just landed a rover on Mars. Perseverance is there, and it's taking pictures, and it's teaching us about the surface of Mars. And so you can see it in the night sky. You can think about the activity that's going on Mars. You can think about the cameras that ASU is using to look and tell us about the surface of Mars, and it's in your night sky tonight. Does that sound good? I knew everybody would like that. I'm just going to leave this screen up. No, I'll close out here. I can never sort of figure out how to gracefully get out of that particular thing. So coming up, there's some things before we meet again, right? We're going to go on daylight savings time this summer. You might or might not know that. Meg pointed out to me today that Sunday is Pi Day. Do you know what that is? 3:14, 3.14 is pi. Okay. Wednesday is St. Patrick's Day. And we have some other things going on, but we will be back with you 2 Wednesdays from now. And it will be just a couple of days after the spring equinox. And so the equinox is very significant. It's a significant thing. It's the beginning of spring. It triggers a lot of liturgical calendars. The Easter Sunday is based on first getting to the spring equinox, and then some things. We'll talk about that next week. We'll talk about how this works, how the sun plays, and how it moves through constellations, and how the sun is moving from the southern hemisphere, crossing the equator from our point of view, and moving into the northern hemisphere to sort of like create the phenomenon that is the equinox, the equal day and night, where we see the sunset on the horizon. And that's really what we're going to be focused on in a couple of weeks. And then 2 weeks after that, we're going to go geo. We're actually going to do an earth science kind of a program because the School of Earth and Space Exploration is about space and about Earth. We've invited another guest speaker, another professor in our program named Dr. Simkin, and he's going to talk to us about just sort of the geology we can see in our neighborhood. What's going on in Arizona? What's Arizona made out of? How did the geology get here? So we've been spending a lot of time looking up at the stars from our backyard and learning about what's going on up there. Now we're going to look at our state. We're going to look at the landscapes and the mountains and all of that stuff in the state of Arizona and take a look at that from a scientific kind of perspective. And so that is 1 month from tonight, four Wednesdays away. We also have something I'd like to announce. We don't do this very often. So one time a year, we have a special day. It's called Sun Devil Giving Day. And it's a big deal on campus, and it's a chance for people to sort of like just kind of register a gift, and then also with that, just kind of like put some appreciation for something that's going on. And so this is coming up. The Sun Devil Giving Day is on March the 18th. It's coming up, and you can actually find it if you go to and I've called your attention to this website before. It's our website, sese.asu.edu, and you'll find a little sort of link. It's called About Giving. And if you choose to do this, and you don't even have to do it on March 18th, it's just one of our trigger dates. It's one of the ones where we say, this is a chance for people that know us, people that are friends, and it's a really kind of low key and pretty easy to do. And so if you'd like to take advantage, Sun Devil Giving Day, March 18th, and that will be also before our next meeting 2 Wednesdays from now. So I think I'll ask you to sort of take a chance to do that. And that's probably the last time you'll hear about it from us or from our particular program. But I really appreciate you do. The school and ASU are absolutely sort of focused on community programs, and we're doing this during COVID right now. So everything's a little bit crazy and a little bit weird. And so if we can kind of help you focus and use that day to focus on maybe participating in giving, that would be super cool. That's really it for today. I want to thank Patrick again. That was a great presentation. It's wonderful that we have access to faculty and they're willing to take their evenings and take their time to put these programs together and follow along with what we're doing. So Patrick, thank you for doing that. And our students, Alicia, Alex, and Spruti, thank you very much for your participation tonight. As always, my colleague Meg, she and I work together on almost everything we do, especially the stuff that relates to public access. And then Kim Baptista for putting the program together. I really appreciate it. You will be getting a survey from Kim in the next couple of days. We really love it when you can kind of give us a sense of how we're doing. If you want to see anything, if you want to hear anything, if you want to know more about what or you have any comments about what we're talking about, please use that opportunity to let us know how we're doing. And I'm going to use that opportunity to say thank you. Go outside tonight. Look at those things we talked about. Find Mars, find that big triangle, earn your MFA, and we'll see you in 2 weeks. Thank you, guys. Thanks, everybody.